Alrighty, well, good evening, friends. Good evening, everyone. My name is Christina, and it is my pleasure to welcome you all to Cafe Sci. Before we get started with our presentation, I have just a few housekeeping items for you. First and foremost, you'll notice the doors you entered in are now closed, but no need to worry. If you have to head out during our presentation, that is a-okay. They're going to stay unlocked for the entirety of the evening, so you can come and go as you please. Also, in the unlikely event an announcement would be made saying we would have to evacuate our space due to an emergency, no need to worry. The way we would actually leave during an emergency, though, would be over the doors over here to your right-hand side of the theater. We'd go out through the front doors of the museum, across our parking lot to the far end. So hopefully we'll all be a-okay. Now for our event tonight, I would like to thank our sponsors for Cafe Sci, which is presented by PPG and sponsored by Cook Myocyte. Cafe Sci is also supported by you all, our dedicated audience. If you'd like to support Cafe Sci, please consider bringing a friend or three next month or donating when you register online. Remember that you can find tonight's presentation on Carnegie Science Center's YouTube channel later this week. Please share it with anyone you think may enjoy Cafe Sci. Now on to our tonight's speaker. Dr. Rana Zakerzadeh is an assistant professor of biomedical engineering in the Rango School of Health Sciences at Duquesne University, where she has been a faculty member since 2019. Dr. Zakerzadeh received a PhD in mechanical engineering at the University of Pittsburgh and completed a 3-year postdoctoral fellowship research in the field of cardiovascular mechanics at the University of Texas at Austin. Dr. Zakerzadeh has spent most of her academic career analyzing and modeling blood flow in human arteries and blood flow through the heart and heart valves. She has collaborated actively with researchers in several other disciplines, particularly applied mathematics on modeling of multi-physics problems with applications in life sciences to help with medical decision-making. Without further ado, please join me in welcoming Dr. Zakerzadeh.
Thank you so much. It's so great to be here tonight. Actually, when I've been told to give this presentation, I was thinking it's virtual. And when I heard it will be in person, I thought, oh my God, that's great to be in person and could see people and interact with them. So this first slide basically summarized the introduction and the background about where I'm coming from and my field. Yes, it works. So I got my bachelor and master degree in biomedical engineering back home in Iran. And this is a picture of me and two twin brothers many, many years ago. I really don't want to say how many years because then you can count how old I am, but many, many years back. And this is the same order of us, again, me and two of my twin brothers, now here in US. I came here for my PhD. I studied at UPitt for mechanical engineering. And then after that, for a few years, I went to Texas, Austin. I was a researcher there, and I was working on designing different prosthetic devices for heart valve. And then after a few years of research, now since 2019, I'm back to Pittsburgh at Duquesne, and I'm teaching and doing some research on cardiovascular devices. Honestly, I like Texas, but couldn't stand the heat, so I'm so glad to be back to Pittsburgh. As you saw, mostly like my background, either the degree that I got or the field I was working on involved the field of biomedical engineering. And usually I've been asked from people who are not engineers that what is it and how it is related to engineering or medicine. If they have to go to medical school or they have to go to engineering school to enter the field, or sometimes that we have open houses at Duquesne, they come to us and they ask what kind of job they can get in the future if they choose this degree. I don't want to go too much through the reason of choosing biomedical engineering as my career, but I just want to give a quick background that it's a combination of both in a good way. They learn to think like a physician, a doctor, but they act as an engineer. And if you look at it, it's really a balance of both you look at the mathematical problem, but also with a view of bio problems. And definitely because of the engineering part, you need to get involved heavily in mathematics in most cases. So the plan that I was thinking would be nice for the talk today is first to think about really how engineer can help doctors to save lives, what has been done before, and what are some perspective that we can use to apply the engineering to the healthcare challenges. And also at the end, I wanted to summarize some of the research that I'm doing and the future of the field. And just like this picture that I had at the bottom is probably, you see something similar to this by the end of this talk quite a lot. But the process is really like a game, it's simple. We try to come from the real design of the biomedical system to a simplified version so computers can solve that. And then we solve this in the computers with some mathematical formulation and computer solvers. And this is what we get as a result. So what this is, we get it to that part later. So using engineering in medicine is not really, like, if you want to think about it, it shouldn't be really that difficult. We basically plan to use the principles of engineering to medical field. And these principles can be applied in variety of the cases. Like if we are thinking of design of some prosthetic devices, or the rules of the thermodynamics or fluid mechanics. And I usually give my student a simple case of like fluid dynamic, that because you can apply it in all the day of your life. When you get up, you take a shower, you drink coffee, you use the water in a sink, then for breakfast you have coffee and you mix the milk in it. In all of them, you can see the real application of fluid dynamic in your life. And same for biomedical engineering is the same thing for the blood flow in the cardiovascular system, in your respiratory system, for phonation, or for the urinary system. So for all of those things, you can see different applications of fluid dynamics. And with all of these things, it comes also the strengths of material, again, for the design of some prosthetic devices, that they can all make together a nice applications of engineering in medicine. And I listed again some of the wide variety of the cases we can consider, like cardiovascular engineering, in neuroscience, for the cellular engineering, especially for imaging. Again, I get to that part soon later, CT or different kind of imaging. And of course, for the design of medical devices and some prosthetic devices or orthopedic devices. And also the surgical robotic devices. I have here kind of a funny image of that because they're doing a surgery on a sandwich, but they can really train these devices these days to do some surgeries that surgeons, not that they can't do, but it's tedious for them to do, or it's just so precise for them to do. And this could be a great help. What I really want to emphasize here is that they really never claim that the engineering part tries to make the role of doctor less significant, because that never would be the case. It's still, that's the human brain, and that does the perfect job. But they try to help them and just make the process easier for them. Oh, and also at the end, I have some drug delivery systems that I talk about it also within my talks. So within the engineering in medicine, we also have a category that how computers can use in medical fields. And I also like to mention that a bit. So basically for most of the therapeutic devices or diagnostic procedures, that's the way that we can also have the role of computers in medical fields. We can think of many applications. Probably the one that comes to the mind for most people is once you take some, like the CT cases or the radiology cases for the the systems that they try to find what is the problem inside the body. Or also if they want to think about some planning and performing for the surgeries, like if surgeons want to try to use the robotic devices or computer softwares to perform the surgery. And also in some cases to gather the information of the patients and also for the data monitoring of the patients, that's also when we can use the computers. So these are some applications that comes to the mind and they look easy. I will explain some of them more, but that's not really what I do and what I want to focus on. And I tell you in a bit how. So for the imaging part, you can really, using computers, get these very, very precise and pretty images. And what engineering does in this respect is that they really try to make the quality of the images, the resolution, and the technology better. So they help in the technology and techniques that they use for these imaging things. I listed this book here because I took the image from the book, and I think that was the very good representation of how engineering could be used in medical fields, especially ML, the machine learning field. But also another picture that I took from the book is this one, which is perfect. You can see that it's quite small, so probably not all people from the floor can read it, but basically we have different examples of the techniques that use with these machine learning tools, we could get these pictures of the human body. Like they have it for brain lesions, they have it for leakage in the respiratory system. This one is retina, the back of the eye. So in the case of, if we have like the blood leakage, again, they can take these pictures and diagnose that. Or here it's a cancer case, it's a skin, and also the lung and respiratory system. So there are all of these techniques that using computers and engineering rules, it's much easier to get them and diagnose the disease easier. Another one that I mentioned that again is a very interesting application is if they use the computers for basically assisting the surgeons to perform the surgery. For a student, once they start to learn the process, it's definitely not recommended to start the process on a real patient. No one wants to be that person, but I think none of us wants to be that person that they tested on us. But with these surgical simulators, they really can exactly experience what happens in that situation, and they learn the process. And once they want to apply it to the real case, then they're definitely much more skilled. And as you see here, like they can do it in different cases. I think here it was knee, and here was vertebra, and also here was some internal organs. But it really feels like the real thing, and it helps the student to train how to be a good surgeon. So we all knew probably some of the previous applications, but most people probably don't know that one of the cool applications of engineering in medicine is that you can really simulate what's going on inside the human body in a mathematical form using computers. And that's what I do, and that's probably because I'm much more fascinated about, and that's what I want to talk about today. The way it works is that I have one very simple example here. So you have a system, how it works, a physics, and computer doesn't know what's going on outside. You basically have to transfer it or bring it to the language that computer understand. What computers see is just big matrices and big forms of the solvers to solve those matrices. So we need to make it as simple as possible for the computer language, but it's still complicated enough because the human body is so complicated. In this case, we were looking at the hyperthermia. We tested device, but we tested drug in mice, and we were looking at these network of vasculature. The plan was to see that after the injection, after like certain time, how would be the temperature inside the body, because the plan was killing the cancer cells. So this is the mathematical part, the mathematical formulation. And just to show you, I really don't want to get into the mathematical part of it, but something like this is how it looks like. This is the language that computer can understand. But still, the geometry is complicated for computer. So we discretize this geometry into very, very tiny small pieces that we call this mesh, the discretized domain, the mesh domain. And then we solve this equation on all of these small pieces. And then we gather all of them together, and this is what we see for the contour of concentration of that drug after certain times. So this is the process of simulating a physical phenomena inside the computer and getting the result that we hope we can validate that with some experiment, because they cannot stand by their own. I personally do not trust computer. So I really hope that in some cases I have also some experimental evidence, so I see that if my model can match well with those as well. So there are mainly two purposes behind modeling this biomedical system inside the computer in a mathematical form. The first one is that we want to investigate the mechanism behind some pathological state. Like we know that heart valve should work this way. This is the function that it should have. And then we want to see that why it doesn't work the way that we expect, or what should be the condition that it works the way we expect. You might see later, later it might connect all together and you see what I mean, because if you talk about the human body, it's not always easy to bring the system out and do the test inside the lab. So the computer is a great help because they can simulate the same thing, but you really, first, it costs zero, nothing, except the people who work on it, they should get paid. The student should pay them too. But beside that, it costs zero, but it provides the same result. And also the second one is that probably it can be more tangible if you want to design a medical device. Again, in this case, if you want to design a device, usually the first design is not the best design, but how do we know that? Should we implant them in people and see how they react? Or should we just test them even in lab? It's costly. If you want to test like 100 design in lab, it's costly. But with computers, you can design them 40 times, 50 times, 100 times, apply the same load that you expect it insert on inside the body, then simulate the procedure, see what's the outcome, and based on that, guide the design of that surgical procedure or that prosthetic devices. So in this respect, we can look at different systems. We can look at the muscle and bone system, we can look at the brain and spinal cord system, or we can look at the cardiovascular system. And this is the one that I know more about and I want to talk about today. Also, in the case of biomedical application, I just listed here some very nice, cool application, and look at it in the two categories that I said. First, to see what's going on behind the real system, like why the system behaves the way it does. And also the second one, guide the design of the medical devices. So like the top category is if you want to see how the valve or why the valve works the way it does. And also we learn something from there that then we guide the design of the prosthetic valves. Or we can learn of the design of the kidney and the urinary system, and then guide the design of dialysis system. Or we can learn how like the respiratory system works, and from there guide the design of the drug delivery system for the respiratory system. And many different applications similar to that. So as I said, I mostly work in the cardiovascular field, and basically I develop computational models, different ones, to help with medical decision making and also help with the design of some medical devices. And in particular, two main projects that I've been involved, and I want to go through some part of it today, is that for the blood flow through the heart valves, and also for blood flow in arteries, both the healthy ones and the diseased ones. giving a bit credit to the student who I work with. So this is my lab at Duquesne, computational biomechanics lab. And one good thing about computational lab, guys, is that even COVID didn't shut us out. We could work because we were just working with computers and we could connect to the computers from home. So our lab still could do whatever we were doing before COVID. And in some sense, we actually became more productive. So it wasn't any problem for us. And this is a meeting that we had at a time on Zoom. So there are some students, but right now, of course, there's some stuff that usually is better to discuss in person. So we are back in campus. And with the students also, whenever we are trying to think about the design of the heart valve or design of the prosthetic devices for the blood flow vessels, I always suggest that start as a simplified problem. Just look at it as a game. How could be the simplest way that you can simulate the problem? And the reason is that it's so hard to debug those computational codes if you start big. So it's always best to start small and then we build on that to finally simulate what's going on in the real case. This is the process, actually, the process that I just mentioned. Formulating the model, and it comes from a conceptual model. You definitely need to think about the assumptions that how to simplify that problem. And in that case, once you get there, you can represent what's going on. Like what I mean is that it could be heat transfer. It could be mass transfer. It could be fluid dynamics, but it's the generalized type of problem. And then you can formulate it in a shape of a mathematical model. Once you have this mathematical model, you can do the simulations to see how the system behaves. And you definitely need some data for validation as well. And there is a cycle, so you basically need to go through this cycle to optimize your design. Once you see it works, then maybe you want to add something more and make the model more complicated. But basically, after this process and incorporating the bio inside your problem, you're good to present the work. I didn't mention it much, but going from the mathematics to the simulation part definitely needs some computer programming. So depending on what language you are familiar with in computer programming or what tools is more available to us, we need to have also that part in mind, that we need to really think as a computer and talk in a language of computer, and then we can simulate the process inside the computer. It's really the combination of these three fields together. As I said, both math and computer programming are something that is necessary. And this physics part, again, as I mentioned, could be a fluid dynamic, heat transfer, or mass transfer, or whatever that you want to simulate. But then it's been combined with a mathematical form to discretize the problem and solve that multi-physics part of the problem that we have in mind on each of these small pieces. This is the mesh that I was mentioning before. So you basically discretize the domain into tiny, tiny small pieces. Why? Because the whole geometry is too big to solve the problem at. You need to solve it in small pieces and then we bring them all together. And in that case, again, although we are trying to make the problem simple and we are trying to solve it in small pieces, but human body is so complicated. And those equations that I just showed previously, and I'm gonna show later, don't worry, they're very, very computationally expensive to solve. That's where the concept of high performance computing comes in. And again, some people might have heard of it, supercomputers, but if not, just give me a minute and I get also to the concept of supercomputers. So what we need is a combination of three: physics, mathematics, and computational part, which involves the high performance computing, or HPC. So we also need some tools, some mathematical computational tools. And there are just so many of them, but here I just mentioned two that I use often. One is CFD, computational fluid dynamics, which basically means that how we can solve the equations that represent the blood flow using computers. And the second one is FSI. The difference is that the FSI is when we have a coupled problem. We have both the fluid flow and we have the tissue deformation, and they both affect the other one. So the fluid flow changes the tissue deformation, and the tissue deformation changes the fluid flow. So once they're coupled, we call that FSI. And if you see it also in the form of equation, I told you at the end, we get to the very, very big matrix that we try to solve. That's it. It's not this is small, like each part of it might be 100 by 100, million by million matrix. Depends on how discretized you make the domain, how many nodes you have in that domain. And this is the vector of unknowns. At the end, you're trying to find this vector. And the right-hand side is something that is known, probably in human body, for example. It is human blood pressure, 120. Or maybe in the case of phonation, it's the pressure at vocal fold. So the right-hand side is known. This vector V, P of F, Q is a vector of unknown. And this matrix is what you try to solve. And in the coupled problem, the fluid part and the blue part, which is the tissue part, are all in one matrix. While in the CFD one, we just have the fluid part. We just solve for fluid. By looking at this, you can easily see that CFD is much easier to solve, isn't it? The matrix is much smaller, it's much easier to solve, it's much faster, but sometimes it's not good enough. So for some reason, sometimes you need to look at this coupling behavior. This picture that I have here is actually is a nice one. Again, I took it from the book that I have a chapter at this book. So it streamlines basically the path line, the imaginary path lines of blood flow in the left ventricle. So this is what we get with the result of CFD. While once we are looking at the wall deformation, we definitely need to look at the coupling between two solvers. I promised I'd talk about supercomputers. So what is a supercomputer? In simple language, the supercomputer is a computer that has a higher performance than a general computer. Then the question might be, what is the general computer? Honestly, the cell phone that you have right now, 50 years back was a supercomputer. So the supercomputers right now is definitely much more powerful, but the supercomputers back then, and I think actually this year is for 90, 60, or 70, the supercomputers back then was nothing close to even the cell phone. A quick comparison here. So it's Apple iPhone 4 and a supercomputer Cray 2, and you can see that the performance is nothing even close. So the supercomputers is really relative, but in simple language, it's a computer that can do better than the usual computers that we have right now, like the laptops or desktops. At Pittsburgh, we have two very good supercomputers. When I was a student at Pitt, I used both. And one is PSC, I think it's Pittsburgh Supercomputing Center. It's joined between University of Carnegie it's Carnegie Mellon and also UPitt. They both have it and is separate from them as well. So they have Bridge 2, which is a very, very good supercomputer. And also Pitt itself has one supercomputer too that a student and faculty and staff, they can use that. And I thought actually that was a very good idea that they had this night vision of like the sky of the Pittsburgh there. It was very cool. So I think by this time of the talk, and I really don't want to go, if you give me time, I'm going to talk forever. So I don't want to go a long time. I'm good for now? Okay. So I think by this time, people are familiar with what's going on in the background. Like the process was simplifying the problem, then bringing it into a mathematical form, then bringing it into computer language, solve it with computers, and present the problem result. So using that, I just want to quickly show some of the stuff that I've done in the last few years to give you more like a visualized representation of what computers can do. One example is modeling of the aortic valve. And as you guys know, it has 3 leaflets, usually. But sometimes, because of some malformation, it might not. Like we have some disease that it has 4 valves, 4 leaflets, or sometimes 2 leaflets are connected and it has bicuspid aortic valve. In some cases, these valve doesn't function properly forever. Like after a few years, the person needs to get a surgery and get that fixed or get a replacement valve. Or in some cases, the leaflets might get thickened and stiff, which is the stenosis valve. So having that in mind, sometimes the plan then it would be that coming up with a good, durable valve design for patient. And have that in mind that usually, like, if you think about somebody who is maybe 80 years old, 90 years old, if a valve lasts 10 to 12 years, it's good, usually. But if you're thinking of someone who is 5 years old, 10 years old, each time they have to do this surgery, and it's the open heart surgery is expensive. So if we can make the durability of this valve longer, it's a huge help. So this is a model that we have for the valves. And we have the blood flow with Navier-Stokes. We have the arterial wall with the large deformation equations. And we have the leaflets with the hyperelastic thin shell models. And this is the valve inside the aortic root. We try to simulate both blood flow coupled with arterial wall and valve deformation. It's a very, very complicated problem because it's highly nonlinear and they're all coupled. So this is the equation that we had for the shell formulation. And you see, the cool thing is that, that's what I said, so we can really change the design of the valve with computers. I'm playing with it. I change the height, I change the length of the leaflets, and I come up with all of these different designs. And each time I simulate it, and then I see what happens, which one gives me the better outcome. I tried, so in this part, I just summarized like some material properties or boundary condition. And for that, just have this in mind that we want to tell computer that what do you simulate? We want to say that the fluid part is not water, it's blood. And the structure part is not a steel, it's tissue. So we basically need some material properties and some boundary condition to represent what's going on inside the body. But once we do that, then we do the simulation. So we come up from the valve, the prosthetic valve to some computational design of that. Then we put in a solver that I just mentioned, and we see how would be the outcome. And we can try it for different design of the valves. We actually, in the paper that we had, I think we tried for, I think, like 50 or 55, but now here I just show 2. And the metric that we have to say that if it is a good design or not is 2 things. First, the valve should open properly. Second, the valve should close completely. So this is the opening criteria, and this is the closing criteria. The red part shows that the area that the leaflets meet. So you basically can see that in this design, there's some gaps here. So when the valve closes, blood can still come back, which shows that this is not a good design. But design B seems like a good design. Another good thing is that we can basically do this patient specific. That's a very big story. If we get time or in question, I'm going to mention that. But the question is, the valves that are now in the market, there are a few of them, but they are not specifically designed for a patient. They're for all people. And it's been proved that if the valve, then the surgeon tries to fix it in a way that it meets every person criteria or size. But if we can design the valve using computers based on each person geometrical features, it might bring a better result for us. The second problem that I wanted to again talk about it briefly is for blood vessels when we have an aneurysm. And that means that we have a section of the blood vessel which is weakened and therefore is bulged. And we might have a rupture in this region, which is a very, very fatal condition. And most of these blood vessels like this, they have a layer that's called intraluminal thrombus, mostly like 75% of them. And it's not completely known what's going on and if it really, this layer helps to support the vessel or cause the rupture. So in this study that we did, we were trying to use computer to answer this question, because in some studies, some experimental studies, it's been proved that it might work as a support, this layer, which is the thrombus is mostly blood clots and fat. But in another studies, they were saying that because it's the barrier, it might really cause the diffusion of oxygen to the blood vessel to become less. Because of the less oxygenation, then the blood vessel weakens, and at the end, it ruptures. So to answer this controversy, we were trying to use some computer models. And again, the same procedure that I said. So we had a complicated geometry at first that the bulge part is just here. So what should I do? Just cut it, because I really don't care about the rest. It just makes the computational part mostly like extensive and much more work. I just cut it and I keep the region that I care about. And then I bring it into the computer language, this meshed part. And here I zoomed in so you can basically see that the pink region is for the blood mesh and the grayish region is for the tissue mesh. Then I solve it in the computer, and this is what I get for the flow streamlines and also for oxygenation inside the tissue. The previous one was just one model, but we can use different patient models and see what happens on a patient-specific basis. So for 3 different patient cases with 3 different thrombus, which is the red section, like the red region here. Again, I performed the same simulation. I solved the equations for blood flow. I solved the equations for oxygen transport, which is mass transport equation. They're all coupled with the wall deformation, and this is the result that I get for each patient. And the plan is that, let's look at the big picture, like what's the plan? I really don't want to, at the end, like each person doesn't help me the result. But if we have a big library of them, then surgeon, based on putting them in some categories, might help them to make a decision that if the surgery can be performed or not, or should be performed or not. A small library might help more in a research, but the plan is having it, for example, for 100 cases or more, and then from there can make a conclusion based on this study. Another work that I was working on recently is for the computer modeling of phonation. And I'm speaking right now, so I can feel it, some tension in my vocal fold. And if you have a career that also involves speaking too much, like teacher, lawyer, salesperson, singer, it's been proved that in usual people, normal careers, about 30%, but in the professionals that have high percentage use of voice, it's 60% in their life, they deal with some vocal fold issues. It's a serious problem, really. And we take it for granted once we talk easily. One thing that we wanted to look at here was that we want to look at the coupling of this time, the fluid is airflow, and the tissue is 2 parts of vocal fold. I wanted to see how it affects the tissue dynamic and also how the tissue deformation affects the voice. We came up with some, this is just a simple work, so we came up with a 2D model, the air channel, and these 2 orange region or vocal fold. Some students were working on the design here, and then again, they imported it, basically they simulated it inside the computer, and this is the result that we see for airflow in the air channel at different times in phonation process. And another problem that we were looking at again, and also this one, the application was a thing that we really cannot get enough information from experimental results, was to design the tissue engineered vascular grafts. These grafts are still not used in the human body, and but they are doing some experiment with that in mice and rats. And the reason is that still they break inside the body. They can't work for a long time. What we can do is that with computer simulation that we work on is that we can really simulate the whole process from the time that we put it inside the body, from the time that it becomes a part of a vasculature, and see what should be the mechanical properties for that. So it can work properly and it has a good matching to the host vessel. Again, we are looking at the equation for the blood flow, equation for the wall deformation, and also here another equation, I call it Darcy, look at it as a filtration through a porous media, because these grafts, as you see here, are very porous in nature. And the final problem that I want to talk about, and again, we did it recently, is that if you want to calculate the pressure drop across a stenosed region, which could be a valve or could be a blood vessel, the motivation is that, well, you might say that, so how physicians and doctors get it right now? There are two ways. One is with angiogram, and it's very painful. If someone has done it, they know. It's invasive, so they actually insert a needle and they capture it invasively. The second one is with Doppler, which is very good. It's non-invasive, but the problem is that it's not accurate enough. Usually it's overestimates the pressure drop, and it causes the surgeon to recommend the surgery even sometimes when it's not necessary. So the plan was using some computer models so we can calculate this pressure drop across the valve, across the stenosed region in artery, and so on. So it could be like below the valve, above the valve, at the valve region, or like different cases. And in this one, I get into those scary equations a little bit. Just to show that it's a lot of equations sometimes, and that's why we say that we need supercomputers, and that's why we say we try to make it more simple and it's computationally expensive. So one is the Navier-Stokes equation for blood flow, as I mentioned. And the second one is that the Reynolds equation. And is that the case if you have a flow that is not really streamlined, or how can I say it, is chaotic, and that's the case in valves. And also, so that part was for the fluid part, but also for the structure part, you're looking at the structure part for the vessel and for the layers of the artery, that it's not homogeneous. It has different layers, each layer has different material properties, and therefore one layer, the thin layer inside the vessel, is modeled with this quarter shell model, and also the thick part of the vasculature is modeled with the Biot model, which could be used for the porous media. And putting them all these equations together, at the end, the plan is that we can help to make a decision for medical procedure that we obtain a pressure gradient that is more close to the catheter one, or also better representation of Doppler method. And we can guide the design for the surgical procedure. So that was the final one I wanted to mention. Of course, if someone wants to discuss more about any of those, I would be very happy to. Some collaborators that I work with, most of the computational work that we did was with PIT Computational Resources, PIT CRC. And also here, my email here, I also have it, I think, in the next slide. So if you want to discuss any of these projects. Also, another thing, if someone wants to hear more of what we do, I think it's 2-3 weeks from now, we have an event here, scientists like me, and we have also a table, again, in the same area. I think it's outside. So we bring some of the students coming with me, and we bring some of the sample of the project or some demos of the project. Would be fun. So I would be happy to see you there too. And beside that, this is my lab at Lieberman at Duquesne. So if you just want to come by, I'd be happy to see you. And with that, thank you so much. I'm taking the questions.
Hi. So when you're talking about designing replacement valves, are those like biologic replacements where you're growing replacement valves, or is that like mechanical replacements that last a lot longer?
About which devices you mentioned?
So when you're designing like replacement biological parts, like is that all mechanical replacements, or is that like
Biological
yeah?
replacement. Actually, very good question. It's two categories. Actually, the one that I just mentioned toward the end, the tissue vascular grafts, that's the part that you put it there, but the plan is that it's so thin and so porous. So the plan is that after a while, it becomes part of a vessel, and you don't see that. But for the heart valves, that's a mechanical part, it stays mechanical. Actually, also the heart valve has two types. So some they made of the tissues, so they're more compatible with human body, but some are purely mechanical, they're made of metals. So, but in both categories, they stay in a body in a mechanical way. So we have some of them, they can become part of the body, but some are purely mechanical, to answer your question. Hello.
Hi. How many valves are in the human body, like all through your system?
A lot of them. So a lot of them. So the heart itself has 4 valves, but usually the problem happens in 2 popular ones. That one is the aortic valve and one is a mitral valve. Because one of them causes the blood to flow through the body and the second one pumps the flow to the lungs. So those 2 are the main ones that usually the problem happens with them. But also beside the heart, I know that in the lymphatic system, like in our legs, we have so many valves. And the same concept that's a great question, the same concept applies to those as well, that you can design them in a way that, I don't know actually, because I really don't know much about it. So I'm not sure if there is a way that they can replace those valves, or they try to cure the problem with some exercises or activities or surgery. But yeah, those valves are counted as a valve as well. Hello.
Hello. I was wondering, you do a lot of research there, which I assume takes a lot of time. But if somebody has an emergency, like an aneurysm rupture, so they need to be operated right away, how close are we from applying a model such as yours, manufacturing the part and putting it into the patient within hours? I mean, how far in the future are we from that?
Oh, your question is how far we are from these methods to really put it inside the human body?
In an emergency.
In an emergency case, we're very far from there. So the short answer is we're very far from there. And part of it, I would say, is still because of the communication between the medical fields and our field, because they don't trust it. They really don't trust what they see in computers. And although I'm making these models, I personally also don't trust it as much as right now I put it inside the patient body. And the reason is all of the simplifications that we made. I said that we really take what it is for granted because the human body is very complicated. And all of these models that I talk about, if you want to represent exactly what's going on in my body or your body or your body, you should really put the condition of each person in the model, which we call it in the mathematical formulation that we do patient-specific. These models geometrically were patient-specific, like I took the medical picture, then I bring it into the computer language, and I basically perform the simulation there, but still the mathematical properties, the blood pressure, those things were not patient. It was a random, or I can say that a usual thing that we used. So we are very far from the stage that we really can use it in an emergency case for a patient, but we are close for designing the medical devices, because that's something that is still, we are further than where the physicians can be. And we need some mechanical part for that. We need to simulate it inside the lab. Experiment can help us. So I would say in that part, we are closer than just deciding what should be the surgical outcome. based on these models.
Hello, your talk, you mentioned how you're modeling the fluid dynamics and the structural dynamics. That's almost treating blood like oil.
Yes.
What about hemolysis, thrombosis, and things like that, where the blood is actually affected by the
Yes.
structures and then affects the structures in turns? How is that
Yes.
picked up in the models?
Yes. That's a very good point, actually. So to not treat the blood like oil, we should look at basically two categories. Sometimes we look at the blood flow in a large vessels, but sometimes we look at the blood flow in a small vessels. For a small vessels, we cannot consider the blood to be Newtonian, while in large vessels, it's been proved that they did some experimental work and like besides computation, because if I want to say computational work, it's not a validation for computation, but experimental work, usually it's a good validation. And they observed that the blood flow in a large vessel like aorta actually is Newtonian. To not treat it like an oil, it's usually you give it the material properties of blood, like the density of the blood and viscosity of the blood. But it's still the more accurate models, they consider the hematocrit, what is the density of red blood cells in the and actually, like I didn't bring it with myself, but we have some calculations of both. Like one time you consider it to be with the red blood cells and one time without it, look at the system more continuous. And you see different results, but if the computation takes 2 more days, the question is this worth it or not? Probably in a larger scale, not, but if you want to be more precise, definitely that's the way to go. You should consider all these small details. Very good point, yeah. Hello.
I just had a question about when you do these models, what's a ballpark of how many elements you'd have when you're trying to model something? How long does it take you to build one of those? And then how long does it take the analysis to be done?
It's a very good question. Thank you. Yeah, I'm getting very good questions. So there is a test for that they call it mesh independence study or mesh convergence study. You start with a coarser mesh and you simulate it. And then you pick a variable to monitor. Probably like in these cases that I said, maybe the velocity of the blood flow at a certain point or shear stress at a certain point. Then I make the mesh finer. Again, I simulate it and I check the same variable. And I see that, oh, that changed. So it's weird. The second time, I make the mesh finer and I repeat the process. It comes a point that the result won't change. By making the mesh finer, you get the same result, but you just have your computer running 2 more days. And that's the point that you pick the coarsest possible mesh that the result won't change. So that's how we decide that. And for all of the works that we do, we have to do that part. That's part of the validation process. Definitely it's the thing that you have to do for the computational work because the quality of the mesh has a direct relationship with the quality of the result that you get. For the second part that you mentioned, that how long does this the modeling and mesh part takes, again, very dependent on the geometry. Usually, like you probably saw, I'm going a few slides back to get to the idealized geometry. Yes, here. Yes, here. So on the top one, I have an idealized geometry, and in the bottom, I have a patient-specific geometry. It's much easier to work with the idealized geometries. It's symmetric, it's easier to mesh that, it's easier to simulate that. That's where usually I start with. For the patient-specific geometry, I would say like probably we have 1 million, more than 1 million mesh at each domain. And the simulation on supercomputer takes really less than a day, maybe 2-3 hours. But if I want to run the same case on my own computer, it takes 3-4 days to run it on this computer. I have one question there. Hello.
So I think there are some cases where when all the valves don't work with the right rhythm, if you have AFib, that you have a chance of getting a blood clot that's greater than a person's whose heart is beating normally. Is your modeling able to determine when flow or non-flow would increase the chances of
For
a
the blood clots? Yeah, yeah. I don't see any reason why not to. If you want to look at the cellular level in those models, perhaps because most of the stuff that I did is in the continuous and the bigger, like macro scale level. But what I presented here is 1%, less than 1% of what computational research is in this field. And I'm definitely sure that there is possible to find a computational model to simulate that. In this case, if you are not concerned of what's happening in the like a smaller scale, yeah, we can have the blood clot. So basically, what we had here, that ILT region here, this red, this yellow region is the blood clot. And we have it as a porous tissue. We can have the filtration from the blood to this tissue. We can look at the mass transport there. We can look at this deformation, or from deformation comes a stress rupture. So we can look at all of these things in a computational format.
Then I have one other question.
Sure.
In some of the engineering fields where I've worked, there'd often be people that would buy commercial packages to simulate something.
Yeah.
But in this case, do you have to really essentially make your own?
Very good question. I didn't mention it, but yes, I use ANSYS for some part of it, but for some part of it, I wrote the code. And just quickly to say that there is advantage and disadvantage of both. Right now, I'm working with very young students in biofield. So it's really hard to expect them to write a computer code in a year. It's impossible. When I was a PhD student myself, it took me 3 years to write that code to simulate something like this. So the rule of thumb is that if what you can do, there is a software out there that can do it as well, then why not? We purchase the software. It's easier to use. But softwares, you can't see what's going on behind the scene. You can't see the background. And sometimes there are some limitations to that as well. So in that case, we should also be skilled to write our own code. It's the balance though. Sometimes, as you said, I'm not sure which software you guys were using, COMSOL maybe? Yeah, COMSOL, ANSYS, they all are the softwares that they can do these kind of simulations, but also sometimes we write our own codes, which is much more computationally or timely costly, but computationally they do the same thing as softwares.
Well, we'd like to thank you for joining us tonight. We appreciate all of your attendance, and we're very happy that you've come. Pay attention online for our schedule for the next Cafe Sci. I believe the dates and speaker chosen should be on our website soon, if not now. So again, thank you guys so much. I want to give a round of applause to our speaker, Rana, there. Thank you. We appreciate you. Thank you for coming.
Thank you.